so let's knock out chapter 16 review. We're going to start on number 5. Let's see, this is version 2. Barium carbonate has a measured solubility at 25 degrees. Determine the KSP. Okay, so first of all, we need to know barium carbonate. Is that correct? Carbonate's a 2-, barium's an alkaline earth. That's right. Okay, so it's going to be in equilibrium with barium and carbonate. All right. So we want to determine the solubility. In other words, we want to know how much of this ends up over here. So the change is we're going to lose some of that. And it's going to show up over here, 1-to-1 relationship. And this is the only equilibrium we need to be concerned with because that's a solid. All right, so we have an X and we have an X. So the KSP, barium has a measured solubility. Oh, we want to determine the KSP. All right, KSP then is equal to X squared, right? X squared. Oh, we know what X is, don't we? 4.03 times 10 to the minus 5. And that's squared to determine the KSP. Yeah, we just need to square that value. Okay, and squared. So we should get 2 significant figures. 10 to the minus 9. Yeah, that was easy. Right. Next, number 6. Mathematical expression for finding the molar solubility of 10,2 hydroxide. All right, so what that's going to do is split up into that cation and 2 hydroxides. So at equilibrium, if we let X be the solubility, we're going to lose some of this. We're going to gain one of these, and we're going to gain 2 of those. Right? So we have X and 2X. And the expression for the molar solubility then would be X times 2X squared, which would be 4X cubed. Yep, 4X cubed. Or 4S cubed. I should be using S because that stands for solubility. All right. About number 11. Which of the following compounds has the lowest solubility in molarity in water? The lowest solubility. All right, first thing I look at is, are these similar compounds? Numbers of cations per anions? No, they're all different. So what we have to do is calculate the molar solubility for each one. to make the comparison. So we've got silver phosphate, and we just did this one. Cadmium sulfide, calcium sulfate, and aluminum hydroxide. All right, each one of these is going to be in equilibrium. Those are all solids. I didn't mark that solids. So we got 3 silvers and 1 phosphate in solution. And then we've got a tin and 2 hydroxyls in solution. And we have 1 cadmium in solution with its 2 plus 2 minus. And then we have a calcium and a sulfate. So these should have similar expressions. And then we have aluminum and 3 hydroxyls. Okay. So the I should have spread out a little more. The KSP for each one of these is going to be, let's do it like this: KSP equals, and then if this is x, this is 3x, so it's going to be x 3x, and that's going to be cubed. All right, so that's equal to 27x to the 4th. Do we have any others like that? Yeah, because this is 3 and that's 1, it should be the same. 27x to the 4th. These two are going to be the same, x squared. All right, 1 and 1. This is going to be, I think we said, well, let's see, x 2x squared would be 4x cubed. Okay, so there we have our equivalents for each of the KSPs. So 1.8 times 10 to the minus 18 is equal to 27x to the 4th. And then 3 times 10 to the minus 27. 3 times 10 to the minus 27 equals 4x cubed. 1 10 to the 28th. 1 times 10 to the minus 28 equals x squared. And similarly with a different KSP, 6.1 10 to the minus 5 x squared. And the last one, 2 times 10 to the minus 33 equals 27x to the 4th. Okay. I'm going to do these first. Solubility in this column right here. So we just need to take the square root of that one. And that's 1 times 10 to the minus 14. And square root of this one is 7.8 times 10 to the minus 3. And I might as well go back to the top. 1.8 minus 18. Then I'm going to divide it by 27 and take the 4th root of it. So that means on my calculator is to the power of 0.25, which is 1.6 times 10 to the minus 5. Then for this one, I'll divide by 4, and then to the third root, which on mine will be 333. 9.3 times 10 to the minus 10. And these are all in molarity. And then the last one, 2 exponent 3 divide by 27, and then take the fourth root. This is 2.9 times 10 to the minus 9. Okay, what was the question? Lowest solubility, smallest number. So let's look at the exponents first. Minus 9, minus 14. This is it right here. That's what I call Henry Ford assembly line. Set it up, do the same calculation, similar calculations all the way across, and then plug in the numbers. Okay. Number 13. The molar solubility of barium carbonate in 0.1 molar barium chloride solution is. All right. Barium chloride is completely soluble. Barium carbonate is not. So we're looking at the equilibrium equation is the one with barium carbonate. Let me set this up before. Okay, only this time, initial change, equilibrium. Only this time, when we lose this much, we're starting off with some barium already. We have a common ion, 0.10 molar, like that. So now we have a different mathematical solution required. All right. So 1.6 times 10 to the minus 9, 0.6 times 10 to the minus 9 equals x times 0.10 plus x. Now, if we leave it like that, we're going to have to solve a quadratic. So with a 10 to the minus 9 KSP, I would expect this x to be extremely small, which would estimate it at 0.10 x. And that makes x divided by 0.1 is 1.6 times 10 to the minus 8, right? Oh, I went the wrong direction. Let's do it longhand. 1.6 times 10 to the minus 9 divided by 1 times 10 to the minus 1. Oh, no, I had it right. 1.6 times 10 to the minus 8, and that answer's not up there. I threw myself a curve and fell for it. All right. Okay, next. 17. Which of the following solid salts is more soluble in 1 molar hydrogen ions than in pure water. All right, if we're trying to solubilize a salt and we're trying to do it with acid, which part of the molecule are we focusing on? Hydrogen ions are positively charged. So we have to look at the negative, the anion of the compound, in order to assess whether it's soluble or not. And if we look at each one of those, hydrogen chloride, for the first one, hydrogen chloride, that doesn't affect the solubility of sodium chloride at all. Carbonate, yeah. Carbonate is a very, very strong base. The reason for that is if we go back to the acid, and this is overall, right? We've got 2 hydrogens here, so 2 minus. This would happen in 2 different steps. But overall, this is a very, very, very weak acid. So this is an extremely strong base. And because that's a strong base, if we do this to it, then we're gonna remove those carbonates from solution. Right? They're gonna be converted into carbonic acid, and which is completely soluble. But what that does is it removes carbonate from this equilibrium. Oops, not 2, just 1. All right. So if we're removing that carbonate through this reaction, then we're going to drive the solubility to a higher amount. So we've already looked at the chlorides. The nitrates the same way. Nitric acid is completely soluble. It's a strong acid. So we're not going to get any effect on any of the other compounds, only the calcium carbonate. That's what you do if you want to solubilize a salt and you want to use acid, then that has to be a strong base. All right, number 19. Let's see, you have a solution consisting of 0.1 molar chloride and 0.1 molar chromate. And you add 0.1 molar silver nitrate. Given the KSP for silver chromate is 10 to the minus 12, and for silver chloride is 10 to the minus 10. Which of the following will precipitate first? All right. The temptation here is to go to Q and compare it to the KSPs. But that is a method for different metals. Right? Here we got the same metal. So what we have to do is we have to look at the molar solubility for each one in the given solution. All right, so we're going to compare silver chloride and silver chromate and find out what their molar solubilities are in that environment. 0.1 molar silver nitrate. We're focused on the anions. That's what I'm trying to say. All right, so we've got, let's separate them over here. We've got one is silver chloride. All right, and the other one is silver chromate. Be proper. Okay. So if we set up our ice table, then we know that we're starting off with a certain amount of silver, like 0.1 molar silver, and nothing here, and 0 there. All right. So which way we're going to move? Got to go this way because there's no chloride. So that means we're going to lose some here. That means one of these is going to show up here, and another one is going to show up there. 1 to 1 to 1. That doesn't work here. So we have 0.10 plus X, and this is X. And on this side, if we lose one of these, then we're going to end up with 2 over here and 1 here. So that's X, and this is 0.10 plus 2X. Okay, so the solution for the, we're comparing the solubilities. Which one will precipitate first is the one that is the least soluble. The least soluble, let's see. Let me read this again. Yeah, you're adding silver nitrate dropwise. Okay, so as you're adding it dropwise, the one with the lowest solubility is going to precipitate first. So let's find out what the solubility is. That is, what is X for each one? All right, so silver chloride is KSP of 1.6 times 10 to the minus 10. And that's 0.10 plus X. Yep, times X. And the expression for this one will be 9 times 10 to the minus 12. The temptation is to look at these values here, say this one's first, but we have to just determine what that is in order to answer the question. 0.10 plus 2X times X. Since each one is very small value, we're going to say that this X is very small compared to that value. So this is going to be approximately 0.10X. And this one is going to be approximately same, 0.10X, right? All right. So we're going to divide by 0.1, which means 1.6 times 10 to the minus 9 molar solubility. And this is 9 times 10 to the minus 11. Did I do that right? I did something wrong. Let me see what I did wrong. It's got to be simple. Oh, you big dummy. This one is squared. Right? So I can't say this. That would be like just comparing these values. This term goes into the expression as squared term. So can I simplify it any further? Well, yeah, we can still simplify it. We can say this one is going to be approximately 0.10 squared times X. So this is 0.1 times 0.1 is 0.01, isn't it? 0.01X. This one's okay. This one we need to divide by 0.01 or 10 to the minus 2. Yeah, 1 times 10 to the minus 2, which would be 9 times 10 to the minus 10, right? That still doesn't work. Oh, we're adding it. I'm sorry. We're adding it dropwise. I was making it more complicated because that's not the starting concentration. The starting concentration is 0, right? Yeah, because we're titrating it dropwise at a time, right? So this is still simply x squared. Stupid mistakes. Is 1.3 times 10 to the minus 5 molar solubility. And this one starts off at 0. And that's 2x squared times x, which would be 4x cubed. Okay, so 4 into that one. And take the cube root. So this is x equals 1.3 times 10 to the minus 4. Okay. So silver chloride will precipitate first. As we add silver to it, it has the lower solubility, and it's going to come out of solution first. The way I was trying to solve the problem was coming at it from the wrong direction. That never would have answered the question. Well, it never did. How many moles of calcium nitrate must be added to 1 liter of 1.82 molar potassium fluoride solution to begin precipitation of calcium fluoride 4? For calcium fluoride, KSP is 4 times 10 minus 11. All right, so the question is how many moles of calcium nitrate? We calculate the concentration first, and then we can back calculate to the number of moles. So the equilibrium is calcium fluoride. That is a solid. In fact, one of the instruments I used to use, the inductively coupled argon plasma spectrometer, used a calcium fluoride window in the spectrometer part because it was transparent to ultraviolet radiation. But it would become clouded over time because of the heat and the garbage that it was exposed to. So we'd have to clean it. And we have to be very, very careful. It is a solid, but it's a very soft solid. So it's easy to scratch. You don't want to scratch anything in your optics. So we've got 2 plus and 2 fluorides. All right. So what we really want to do here is determine the solubility. To begin precipitation means what's the minimum amount of fluoride as 0.182 molar potassium fluoride that we add. So if we set up our ice table, then we want to see what's the solubility here. And it's going to produce one of these and two of those. All right, so X, 2X. And we're starting off with 0 because we want to determine the solubility first. And then we can determine the ratio of calcium and fluoride to answer the question. All right, so the KSP is 4 times 10 to the minus 11. And that's X times 2X squared, which is 4X cubed. So the solubility is 4 exponent 11 divided by 4, and then take the cube root. That's 2.17 times 10 to the minus 4 molar. All right. So 0.182 molar potassium fluoride. Let's see, how many? This is molar concentration for calcium fluoride. 21. I get a feeling I'm marking up the wrong 3 again. Yes, I am. Yeah. I hate it when that happens. We're actually starting off with, because we know what the concentration of this is, 0.182 molar. So this is plus 0.182. Squared, and we're going to approximate that to 0.182x. So x is actually going to be that divided by, wait a minute, x squared. X squared. So x is going to be the square root of 4 divided by 0.182. Yeah. Square root. 1.48 times 10 to the minus 5. 10 to the minus 5 molar. That's the calcium fluoride solubility. Which relates to the calcium ion concentration also. So if we want to add enough fluoride to balance that, seems like I need another factor in there. I need twice as much fluoride. This is calcium fluoride F2. F2. What's the question? How many moles of calcium nitrate? Oh, calcium nitrate. Yeah, that's the concentration of calcium, and there's 1 calcium per. But why isn't that not my answer? That's 2x. Oh, I'll tell you what, I'm my worst enemy. That should be cubed. Because I got this x over here. No. This is squared times x. This is squared. right? No, start over. Solve it for this. Oh, all I need to do is this one. 10 to the minus 11 divided by 0.182 squared. That's equal to x. X is not squared anymore. Mm-hmm. 1.2 times 10 to the minus 9 molar calcium. And if we got 1 liter, in order to make that molarity of calcium, we need that many moles of calcium added to 1 liter. Am I confusing you guys? Are you seeing how easy it is to make mistakes? Yeah. All right, number 23. Let's see how quick I can mess this one up. We've got 0.01 molar solutions each of lead nitrate, manganese nitrate, and zinc nitrate. Solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? No precipitate form. Okay, this is one where we have different metals. And if we find the Q values for each one, then we can determine whether they precipitate or not. So what we need is to find out what is the hydroxide concentration. We know what the lead, manganese, and zinc concentrations are. So each one is divalent, right? So we have a metal with nitrate, right? Nitrate, which is going to produce that for each one of them. What we want to do, and we know the concentration of each one of the metals is 0.01 molar. Okay. So what we're actually looking for is, well, that's true for that one. What we're looking for is the combination of each one of these metals with hydroxide. So we have M2 plus 2OH minus. What we need to know is what's that concentration at 8.5 pH. So if the pH equals 8.50, the pOH equals 14 minus 8.50, which is an 8 from 13, 5.50, right? And then the OH concentration then will be 10 to the minus 5.50. Which is 3.16 times 10 to the minus 6. All right, so if we have a concentration here of 0.01, and we have here 3.16 times 10 to the minus 6 molar. I thought I was on the right track. Okay, that's right. Oh. This is the same. This concentration is that concentration. Right? So this goes over here. Now we can do the Q for each one. Well, actually, we got one Q value that we're going to compare to each of the Ks. So far, so good. Okay. So what would be the Q here? Well, it would be 0.10 and then 3.16 times 10 to the minus 6 squared, right?
It's the right number. 0.10.
It's 01. Thank you. There we go. I stand a better chance of getting the right answer now, though. Let me square that. And then 0.01 times that. So the Q is 1 times 10 to the minus 13. All right. So the lead hydroxide, manganese hydroxide, and zinc hydroxide, KSPs. KSPs for each one of these. 10 to the minus 20. 10 to the minus 13. And 10 to the minus 16. Okay. We'll get precipitation if the Q is greater than the KSP. So this one is greater than that KSP. This one is less than that KSP by just a little bit, and it's greater than this KSP. So we're only going to get precipitation of lead and zinc. And that would be D. Oh, that's one that you wanted to do, wasn't it, Shania?
Yes, it is.
Okay. Does it make any sense?
It does now, because when I was trying to do it on my own, I was getting confused.
Okay. I can bear witness to the confusion. Let's see about 24. Okay, 24. Ooh, that's getting kind of weak. In the qualitative analysis, for this scheme, how are the analytical group 2 cations separated from 3 through 5? Okay, separate. Oops, that was completely dried out. We want to separate group 2 from 3 through 5. Okay. You're going to have access to this chart right down here. So how do we separate 2 from 3 through 5? Well, here's group 2, and we separated it by using acidic hydrogen sulfide. Well, the reason we did that was to decrease the concentration of sulfide, and that would take out the least soluble sulfides of the groups of the different elements. So let's go back up to 24. Addition of H2S in acidic solution forming insoluble metal sulfides. That's the one, C. Okay. Now that, of course, if you're separating 2 from 3 through 5, that means you've already separated out group 1. Otherwise, you're going to get a combination of 1 and 2. Okay, 25. Which of the following solid salts should be more soluble in 1 molar ammonia than in water? Well, the only one we've studied that forms a complex ion with ammonia is silver. Potassium, sodium, potassium or sodium won't form, and it's not needed. Well, potassium nitrate is completely soluble. Potassium chloride is completely soluble. Sodium carbonate is completely soluble. Yeah. So we don't need ammonia for any of those. As a process of elimination, you end up with silver bromide. That's the only one that works. Unless you say none of these. But we know that silver forms a complex ion with 2 ammonias. Let's see. Number 27. That was getting kind of weak too. The correct mathematical expression for finding the molar solubility of lead 2 chloride. All right, lead 2 chloride means that. And it is very sparingly soluble. Aqueous plus 2. I think we've already done one like this. So if we set up our ice table and we're going to lose some of this, then we're going to gain 1 of these and we're going to gain 2 of those. That means the expression for the molar, for the KSP, right? Well, KSP is equal to 2x, x, x times 2x squared, which is 4x cubed. Oops. Wait a minute. Oh, I was looking at the wrong one. D is the right answer. For a minute, I was looking at 28. All right. All right, this is just definitional. We've already used it once. Which of the following leads to formation of precipitate if Q exceeds the KSP? That's all it's required. Greater than the KSP for metal precipitation. All right, 34. Do it. Okay, we're all right. What's the solubility of silver chromate in 0.049 silver nitrate? All right. I think we've done something like this before. Solid. 2 silvers plus chromate. All right. And what are we starting with? We're starting with 0.049 silver. 0.049 molar silver. Nothing there. So we're going to lose some of this. We're going to end up with 2 of these. And we're going to end up with 1 of these. Okay, so that's X This is 0.049 plus 2x. And then 9 times 10 to the minus 12 is equal to this one squared times that. And we're going to say that this is small enough so that we can eliminate that one and just square this one times x. So to solve for x, we need to divide this by the square of that one. And there it is, and divide it into 9 times 10. Oops. Exponent. And I get molar solubility of 3.7 times 10 to the minus 9 molar. Yep. Those are fairly straightforward. Let's see. 36. How many moles of calcium fluoride will be dissolved in 3 liters of 0.089 molar sodium fluoride solution? Oh, I got a sneaking suspicion. Okay. I don't think I'll make the same mistake twice here. The solubility, we're looking for the solubility. In order to get the answer, we need the solubility first of calcium fluoride in that solution. All right, so initially, 0.089 fluoride, sodium fluoride, 0.089 molar here. And we're going to lose some of this and end up with some there and 2 here, plus 2x. Right, so 4 times 10 to the minus 11 is the KSP. And that's equal to that x and that term squared. So it's 0.089 plus 2x squared. And since we already have a common ion in there, we can expect this to be a very small value. So it's going to be 0.089 squared times x is equal to this. So this will give us the solubility, but it won't answer the question yet. 0.089 squared and divided into 4 exponent 11. So that's x equals 5.05 times 10 to the minus 9 molar. All right, but we're in 3 liters. How many moles of calcium fluoride will dissolve in 3 liters? This is the solubility of calcium fluoride, or the calcium ions. So if this is the molarity, then we multiply times 3 liters. That cancels liters because this is moles per liter. Cancels the liters and leaves us with moles. Times. So this should be 1.5 times 10 to the minus 8 moles. Okay. Did I lose somebody? This is calcium fluoride. This is the volume, and this gives us moles of calcium fluoride. Saturated. Okay, 37. This goes back to our selective precipitation chart. We should be able to do this one without having to scroll to it. What's the best way to ensure complete precipitation of tin sulfide from a saturated H2S solution? Maybe we better go back. We got a saturated from a saturated H2S. Okay, precipitation of SNS using hydrogen sulfide. Well, the best way is to get complete precipitation is to have the very highest concentration of sulfide. Right? And we know if we do it in acidic solution, it's going to be very low concentration. But if we make it basic, this yields 2 hydrogens plus sulfide. If we make it basic, then we're removing these hydrogens into water, and that increases the sulfide concentration and guarantees 10,2-sulfide will precipitate. Right. So we need to do this. We had to add a strong base to this solution, like sodium hydroxide will do great. All right, number 40. It's going downhill fast. Pull out a fresh one. The concentration of magnesium ion in seawater is 0.052 molar, excuse me. At what pH will 99% of the magnesium be precipitated as the hydroxide? All right. If we're going to precipitate magnesium as the hydroxide, the reaction is going to be this. All right, let's do it this way. We'll do our solubility. Hydroxide, we need 2 of them, solid. This is magnesium 2 plus and 2 hydroxides. Okay. If we know the concentration of magnesium is 0.052, so our initial concentration is 0.052, but we only need 99% of it. So we'd multiply that times 0.99. And that'll give us our target concentration for magnesium, which is 5, it's like 6, 5.15 times 10 to the minus 2 molar. Okay. Now, at what pH? Well, if we're going to precipitate all of that, we need the same molarity. No, hold on a second. If we're going to precipitate all of that, okay, I'm getting confused again. Okay. We know that the KSP is equal to 8.9 times 10 minus 12. And that should be equal to magnesium concentration times the hydroxide ion concentration squared. Right, that's given from the equation. We know the magnesium concentration is going to be 5.15 times 10 minus 2. Right? So we can solve for the hydroxide and get the pH. So let's see, divide this into that. So 12, we'll flip that divide. So the, actually, we need to take square root of it, right? So I got to take square root of this also. 1.31 times 10 to the minus 5 equals the hydroxide concentration. So POH is the negative log of that value, which is 4.88. And the pH then would be that from 14. 9.1 pH. Or 9.12. Yeah, rounded. There we go. Yeah, two significant figures, so I need two decimal places. All right, that's 40. Oh, 41. 41. A solution containing 0.01 moles each of iodine, bromide, and chloride when the solution is mixed with 200 milliliters of 0.24 molar silver nitrate. How much silver chloride precipitates out? All right, we've got each one of these halogens, silver halides. And since they each produce the same, let's see, silver, let's do it like this. Halide, we usually abbreviate, use a symbol for halides as X. So it's 1 to 1. Right? That produces a silver ion in solution and a halide in solution. That means that we can directly compare the KSPs to see what their solubilities. The first one that's going to be precipitated is silver iodide because it's 10 to the minus 16. Okay, so we can set these up as, and then the next one is going to be bromide. Yep. And then the last one is going to be chloride, 1.6. All right, so if we're starting off with 0.018 moles each, 0.018 moles each of silver, right? It's of silver iodide, silver bromide, silver chloride. So the silver is the precipitating one. It goes with the, well, no, the silver starts off, this is the halide concentration. Right, that's X, 0.018 moles. Well, I got that already. Okay. All right, so this one is going to be completely precipitated, assuming that 0.24 molar, 200 mils of 0.24 molar silver nitrate gives it enough silver. So let's find out how much silver are we starting with. 0.24 molar, 0.24 moles per liter times 0.2 liters. Like 200 milliliters, 0.2 liters. Trust myself. So that's 0.048 moles of silver. Okay. All right. They're 1-to-1, right? So this is going to use up 0.018 moles of this amount. 0.048 minus 0.018. So that's 030, right? 030 moles of silver remained after this step. Then 030 minus 0.018 equals what? 0.012 moles of silver remain. Yep. Well, this amount of silver is going to use up only part of the chloride, but all of the silver is converted into silver chloride. We'll have some chloride left over, but all of it will be this. This is 0.012 moles then of silver chloride at the end, solid. Okay. The question was, how much of that precipitates? Well, there's the number of moles, right? All we need is molar mass of silver, which is 107.87. Oh, silver chloride, excuse me. 107.87 for the silver, and the chloride is 35.45. $35.45. So that's 143.32 grams per mole. 143.32 times 0.012, which is 1.72 grams of silver chloride. Close enough, 1.7. Now, the problem didn't address separating the silver halides in the end. Because if we just dump them together, you're going to get a mixture. But out of that mixture, 1.7 grams of it is silver chloride. Oh, here we got another selective precipitation. So what are we doing? When a mixture containing cations of groups 1 through 3 is treated with H2S in acidic solution, which cations are expected to precipitate? Well, if it's acidic solution, then you're going to get groups 1 and 2, because the acid is going to take out, well, let's see, if it's chloride, if it's HCl, it's going to take out the chloride insoluble compounds, group 1s, and then we add a H2S in acidic solution. It's going to take out the second group. So we're only going to get groups 1 and 2. And you'll have access to that chart, so you know, if it doesn't come to mind, you can go look it up. All right, 46. This looks like a challenge to me. Cation M2 plus reacts with ammonia to form a series of complex ions. Oh, okay. It's not as bad as I thought it would be. Right, it goes through different steps. One ammonia associates with it as the Lewis base, and then another ammonia associates, and each of the Ks are given, and then the final ammonia associates. So this metal associates with 3 ammonias. A 1 times 10 to the minus third mole sample of MnO32. So that's how we get the metal in solution, is added to 1 liter of 15 molar ammonia. Choose the dominant species in this solution. That little blurb right there before the answers is blue smoke. All we need to do is look at the equilibrium of each one of the reactions. And if we go through each one, we find that the first addition is going to go essentially to completion. K is 100. Then K is 1,000. K2 is 1,000, and K3 is 100. So if you put all those together, 3, 4, 7, that's 10. The overall K equals 10 to the 7th, which means that reaction is going all the way to the end. So your dominant species is going to be the one with 3 ammonias, which is D. Let's see. Yeah, there is kind of squirrely. There's a squirrely one in there, that E. Just to see if you're paying attention. That's nitrate. There's no nitrate in there. Now, nitrate can be a ligand for some metals, but not in this case because there was none there to begin with. And we retain the charge because ammonia is neutral. So we look at the Am2 plus, we have to have that 2 plus charge in there for the final product. Okay, 47. What is the concentration of nickel 2 plus in 0.045 molar nickel nitrate solution that is also 1 molar in ammonia? All right, this one I think, and we're given the formation constant of the hexamine nitrate ion. And I think I know how to solve this. Let me refresh my memory. Oh, 47. I was looking for the wrong one. Yeah, okay. All right. This is one of those like our acid-base chapters, where it's best to go do the stoichiometry first, like go all the way to completion and then work your way back as an equilibrium. So what we've got is 6 nickels. What's the charge on that? 2 plus. And then 6, wait a minute, 1 nickel, I'm sorry. And 6 ammonias. There we go. And this produces nickel and ammonia mixed with a 2 plus charge. Okay, there's our equilibrium expression. If we go, what are we starting with, right? This is a stoichiometry, start, finish. So we're starting with 0.045 molar nickel. nickel nitrate. Since there's only one nickel per, then it's 0.045 molar. 0.045 molar. And the ammonia is 1 molar. Okay. Now, okay, so what's going to happen? Well, what's 6 times this one? 3, 27, 2, 0.227. See, did I do that right? 3 and 24 is 27. Okay. So that's how much is being used up. Well, we're going to use up all of it actually. Minus 0.270. We're going to use all of this up and some of this. So that gives us 0.73 molar remaining for our equilibrium. Okay. That's how much ammonia is used because it's 6 times this concentration. Right. And the finish is going to give us 0.045 molar because it's 1 to 1. Start off with 0, 0.045 molar. So those are our starting points for the equilibrium. Okay. All right. Let's see. Initial 0.73 molar. 0.73 molar. And initials 0.045 molar. 0.04 molar. 0 here. So the change, in this case, now it's going to go back this way because that was 0. So if we lose some of this, it shows up over here, 1 to 1. But we're going to get 6 of them over here because it's 1 to 6. All right. So at equilibrium, we'll get, and this is all in aqueous solution, so we have to include everybody. This gives us an X here. This gives us 0.73 plus 6X, and this gives us 0.045 minus X. Okay. The formation constant is 5.5 times 10 to the 8th. 5.5 times 10 to the 8th equals what? Well, it equals 0.045 minus X divided by X times 0.73 plus 6X. Okay, am I going to have to do a quadratic on this one? It looks like I've approximated it. Is that 10 to the, that's 10 to the 8th. Oh, okay. So with this large value, we're saying that the transition back this way is going to be very small because it wants to be on this side. So you're only going to lose a little bit of this and you're only going to gain a little bit there. So that's why we can approximate it as 0.045 over X times 0.73. And then I put X on this side. And then I bring this over. I'm going to put everything out here before I do the calculation. 5.5 times 10 to the 8th and 0.73. Like that. Then if I make a mistake, we have something to go back and study. 5.5 exponent 8 divide and 0.73 divide. So I get x as 1.12 times 10 to the minus 10. So what was the question? What's the concentration of nickel in solution? 1.1 times 10 to the minus 10. Oh, wait a minute. I did something wrong. What did I do? Oh. Right. That's ammonia. It's ammonia. Has to be 6. Try that again. That's more like it. And notice one of the answers up there was the answer I got wrong. So the temptation is to go with it when I made a mistake, a serious mistake. Okay, number 50. This rag is about full. The Kf for the complex ion diamine silver is 1.7 10 to the 7. Ksp for silver chloride is 10 to the 10 minus 10. What's the molar solubility of silver chloride in 1 molar ammonia? All right, we've got two, in this solution, we've got 2 reactions going on at the same time. We've got the solubility of silver chloride. And we've got the formation of diamine silver 1. So we've got silver aqueous and 2 ammonias is in equilibrium with this complex ion. There we go. And what we want is to calculate the solubility of silver chloride. So they're happening at the same time. So we're within our rights to combine the 2. So the Ksp for this one is 1.6 times 10 to the minus 10. And the Kf for this one is 1.7 10 to the 7. Now let's see, if we combine these, are we going to be able to determine the solubility of silver chloride? Well, the silver ions are going to go out because they're on both sides. We're going to have silver chloride solid, ammonia, complex ion, and chloride in the final expression. Right, so those go out. We could include them, but do I want to? No, I don't think I do, not in this case. So we've got this one solid, and then we've got two ammonias in equilibrium with complex ion and chloride ions. And the KEQ for this one is equal to the KSP times the KF. So we just multiply those two together. .6 minus 10 and 1.7 to the 7th. And I get 2.72 times 10 to the minus 3. Okay. So what are our initial conditions here? Ammonia is 1 molar. Be sure I'm on the right track so I don't waste your time. I think I'm on the right track. Mhm. Okay, so that expression, let's go ahead and write it over here. KEQ is equal to 2.72 times 10 to the minus 3, and that's equal to the complex ion to the first power, chloride ion to the first power, divided by ammonia squared. Okay, so at equilibrium, what are we going to have? Well, I'm not sure. Okay. Hold that for a second. If we're looking for the solubility, we want to know how much of this and that go into solution. Right? So this is going to be like that, or X. Can we relate that to this one? Well, yes, because this is 1 to 1. That's S. This is S. Right? So this is going to be S, and this is going to be S, and this is going to be 1 minus, well, actually, that's going to be 2S, isn't it? Yeah. Okay. I swear we're not mixing apples and oranges. The solubility is definitely going to be S. But we're going to lose, in order to get these S's over here, we're going to lose 2 of those S's. Right, so at equilibrium, it's 1 minus 2S. And that generates only 1S and 1S over here. So we can plug in S here. Well, actually, let's be correct. It's equilibrium. And on the bottom, we have 1 minus 2S squared. And that's going to be equal to 2.72 times 10 to the minus 3. Now the question is, can we simplify it? Do we need to simplify it? No, we don't. Because this is squared, right? So if we take the square root of both sides, then we can get rid of our square. So we're going to end up with s over 1 minus 2s equals, take the square root of that value. That's 5.22 times 10 to the minus 2. Now we can say, all right, let's bring this expression over here. S is equal to 1 times this one and minus 2 times that one, S. Yep. There we go. So now, it's over here as a plus. So it would be, this is 0.104 S, right? So bring it over here as a plus, and we have 1.04 S equals 5.2 times 10 to the minus 2. And S simply is that one divided by 1.04. It's 5. 5 times 10 to the minus 2. 4.7. Did I get a rounding error? Oh. Wait a minute. Divided by a bigger number, it'd be a smaller value. Seven. I didn't carry the number over right. Okay, it's 50. 52. Ooh, this is a challenge. I recognize that one. This looks like a good extra credit coming up. Two. Oh, for this system, 500 milliliters of 0.02 molar manganese nitrate mixed with 1 liter of 1 molar sodium oxalate. That's C2O4 is oxalate ion. Acts as a ligand to form a complex ion with manganese. So the first oxalate combines with Mn2 plus to give you MnC2O4. Yep. And then the second one combines with that one to give you MnC2O4 taken twice to the 2 minus power. But that one's flipped, right? So what's the equilibrium concentration of the first MnC2O4? All right. Seems like that second one ought to be flipped around. I'm okay too. Yeah. Yeah, I think that one should be flipped around. Let's do that. Yeah. Let's put them all up here. So the first one, the first ligand, and they're all aqueous, so we're going to leave that part out. The oxalate then combines to form this first one. And then C2O4. And that K equals 7.910 to the third. Then the second one needs to be flipped. I want to go ahead and flip it when I put it on the board. So we're going to take that one, MnC2O4, plus another C2O4 2 minus. And that gives us the last C2O4 2 minus. And this K then is going to be the inverse of that K because we flipped the equation. So we just need to take the inverse of 1.26 10 to the minus 2. And invert it right there. So this is 7.94 times 10 to the first power. Okay. Now, what else are we given? 500 milliliters of 0.02 molar manganese mixed with 1 liter of 1 molar oxalate. Okay, find the equilibrium concentration. I think we need to let this one go to completion and then work our way back. Yeah, what's the initial concentration of manganese? Initial of manganese, I better do this, manganese. So the initial concentration of manganese, before we do anything else, is 0.02 molar times 500, or 0.5 liters. So 0.02 molar times 0.5 liters. So half of that, 0.010 molar manganese. So far, so good. Well, actually, that's how much we put in solution. We got 1 liter of the other one. So this is, excuse me, this is moles. So if we divide that by half a liter, and 1 liter is 1.5. So this is the initial concentration of manganese before any reaction occurs. 0.01 divided by 4.5. That's 6.67 times 10 to the minus 3 molar manganese. Okay. How about the initial concentration of the oxalate? It's 1 liter. Okay, 1 molar, 0.1 molar times 1 liter let's divide it by 1.5 liter. So that's 1 into 1.5. So this is 6.67 times 10 to the minus 1 molar oxalate. There. That's the initial concentrations of our reactants. Okay. All right. So we know that this is going to go virtually to completion, and this one also virtually to completion. So when we react this manganese with that, we're going to use 2 of these, right? We're going to use 2 of those for each one of these. So we're going to use up twice this much of that. Does that make sense? So this is 1.33 times 10 to the minus 2, and that's how much we're going to use up of this one. Subtract that from, so 6.53 times 10 to the minus 1. This is initial, and we used all that up. Okay. Okay. So this expression right here is equal to, the equilibrium expression here is equal to that value. 7.9 times 10 to the first power equals, and this is going to be MnC2O4 minus, and this is going to be MnC2O4. This is going to be C2O4 2 minus. So what we're saying is at equilibrium, right, we used up, right, we used that up. And this is, which one is this? This one right here, right? That right there. So that one goes in here. 6.53 times 10 minus 1 goes there. This is our unknown. That's what we're solving for. And then this one is 1.33 times 10 minus 10. Okay. So that's equal to 79, right? 794. 79.4. Okay, let's bring this over here, bring this one over here and do that math. 33 equals 2 and 79.4 divide and 6.53 exponent divide. So I get x equals 2.56 times 10 minus 4 molar. Is that even close? No. Definitely get a. Oh, wait a minute. That's not right. That's what I subtracted from this one. That's the wrong value. This is that one right there. 6.67 times 10 minus 3. Everybody see where I made my mistake? Okay. Six point three, and then 79.4 divide. So that's 1.3 times 10 minus 4 more. That's the concentration of the first product. Some days are good and some days are bad. I fell victim to a messy board. What about this one? 53. What's the molar solubility of lead chromating 0.05 sodium thiosulfate for, okay, and lead chromate has that KSP and the KF is 2.2. That's what I thought. Okay. We did one like this a little earlier. We've got two reactions going on at the same time. We want to know what the molar solubility of lead to chromate is. So lead to chromate, right? And this is a solid. It's going to produce that in solution, and it should be two. No, one of them, because that's 2 minus. Yeah, that's right. Okay. And this KSP equals 2 times 10 to the minus 16. And then we're going to take those these lead ions and combine them with thiosulfate. So sodium is a spectator. Thiosulfate is a 2 minus charge. So we're going to have lead 2 plus and thiosulfate minus, and that's going to produce this complex ion. Neutral. And the KF for this one is 2.2 times 10 to the 6th. Okay. We're going to need to combine this equation and give us a KEQ here. And that one times out. The leads go out. We're left with CrO4 S2O3 2 minus the 3 of them with a 4 minus. Excuse me. 3. Good thing I checked, double checked. Okay, now this is 3. And this is plus the chromate. Okay. And the KEQ for this reaction is two exponent 6. I get 4.4 times 10 to the minus 10. So that KEQ is equal to this complex ion. Let's see. Yeah. Complex ion times chromate just double checking myself. Okay. Divided by this term, S2O3, 2 minus to the third power. There we go. Okay. So our initial concentrations we're going to go with what was it, 0.055? Yeah, 0.055. So 0.055, this is initial. And okay, we don't have any of this or that. So we're going to have to lose. We're going to end up, if we want the solubility, we're looking for the lead and the chromate concentration. So we're looking for this one. We're going to add some of this. And we're going to add some of this too, because that's one and that's one. So it's 1 to 1. Right? Okay. But we had to lose 3 of these to get that 1x, because the ratio here. And so now we know that it's 0.055 minus 3x. Now we can substitute some values. This one is x, that one is x, and this one is 0.055 minus 3x. Cubed. All right. That's not going to help us much unless we estimate. Yeah, we're going to have to estimate. All right. This value says that we're not going to go too far that direction. So we can eliminate that one. This is x squared over 0.055 cubed equals 4.4 times 10 to the minus 10. And then we can solve for x. Well, x squared then is going to be this one cubed times that value. 0.055 here 3 cubed times this value. And that's 7.32 times 10 to the minus 14, and take the square root of that. 2.7 times 10 to the minus 7. And we set X up as, so that answers the question, what's the molar solubility? That's X. So that should be the molar solubility.